Hey guys, I'm Kurt. Welcome back to Comp Sci 5. Today we're going to see heaps in action. Last time we got an introduction of them about the operations, and we're going to right now do the two of them in action, live action. Yay! So we got inserting all these elements into the heap, and then we're going to grab the element with the highest priority, aka the one at the root. So let's go through it. So first off, we have empty stuff. So now we're going to start off with 5, which is going to go at the root, you guessed it. 11 is going, and by the way, we're going to prioritize low elements, so it's a mid heap. So 11 comes in, and because 11 has lower priority than 5, we can keep it right where it is. So now 2 comes in, and now the game has completely changed for the following reason. So 2 has higher priority than 5. Since 2 is a child of 5, it violates our min heap property, therefore we need to bubble it up, which means we need to switch this one and this one, making our heap now 2, 11, and 5. Super. So now we're going to go on to 17. So we insert top to bottom, left to right. So this is our next available spot. 17 has lower priority than 11. Therefore, we can throw it in right there. So now we have 3 coming in. 3 comes in here, and we see that 3 has higher priority than 11. 3 is lower than 11. Therefore, we need to bubble up again. So now we have 2, 3, 5, 17, and 11. Super. So now we have 7 coming in. And we don't insert it here because we have to go left to right by each level until each is completely filled, because that's what a full binary tree is. So when we go to 5, we can put 7, and because 7 has lower priority than 5, we don't have to do anything. Super. 10 comes in. 10 also has lower priority than 5. Therefore, everything's great. Now this 1 comes in, and now everything is just really, really crazy. It's nuts. This 1 has way higher priority than 17. It has higher priority than 3. It even has higher priority than 2. So it's going to bubble up all the way to the top, right? So first off, it's going to go switch with 17, right? So now the 1 is up here. Then you're going to compare it with the 3. Well, 1 is actually higher than 3, so these are also going to switch. Now the 1 is up here. Now the 1 is actually higher priority than 2, so it's going to switch one more time. So then when we draw our next tree, we have 1, 2, 5, 3, 11. We have 7 here, 10 here, and finally 17 down there. Super. So this is, after all of our insertions, this is what we have. Next off, we are going to do the grab the highest priority element, which is this 1. So we are going to switch our colors, and we're going to grab the root. Boop, we kick it out. We grab the last element in the array, which is 17, and we put it at the root. So now we have 17, we have 2, we have 5, 3, 11, 7, and 10. Now we need to bubble down. So we do so by comparing to each of the children, right? We need to go and decide, well, do the children have higher priority than 17? Well, they both do. They both have higher priority because it's a min heap and they're both less than 17. How do we know which one to switch? Well, we need to take the one with the higher priority. Because 2 is less than 5 and it's a min heap, this has higher priority than 17. So these 2 elements will switch. Now 17 is here. We do the same thing. Lo and behold, both the children have higher priority again. We do this little adjustment because 3 is less than 11. We're going to switch these 2. And finally, we draw it up. 2, 3, 5, 17, 11, 7, 10. So as an array, this right now is our min heap. As an array, because that's what's happening behind the scenes, it's going to look like this. Remember, we keep this first element vacant. And there, this is what it would be in the computer's memory. So a thing to note here is that we have 7 elements total in our min heap, And if you take the natural log of that, it's going to be right around 3, because 2 to the third is 8. So what that corresponds to is the height of this tree. What that ensures is every time you're removing that maximum elephant rather in the array, you heapify again. In order to maintain this property, it's going to be ln of n comparisons to do so, which is really, really good runtime operation. All right, there's heaps for you. There's heaps in action. Comp Sci 5, what a great thing.